Welcome everyone. Yeah. Hello, my name is Bernardo.
And my name is Edgar.
And this is our second partial project about what we can do with derivatives.
Well, in this case, they first gave us a function, and they asked for us to solve some aspects about it, like the domain, x and y intercepts, symmetry, vertical asymptotes, horizontal asymptotes, first and second derivative, and in the case of the first derivative, the ID test, and in the second derivative, concavity test, and at the end, the graph of the functions.
Okay, so first of all, with the domain, here we can't do any more simplifying. So as we can see here, in our denominator, that is what we look for. In order for the equation to not work, x would have to be equal to 1. So then this at the bottom will be 0 and our result will be undefined. So therefore, our domain is when x belongs to all real numbers except of number 1. And that will be our domain. Now, for our x and y intercepts, here we have our function x minus 2 over x minus 1. We'll make that equal to y at first. And then for finding out the x-intercept, we'll make y equal to 0. Then here the x minus 1, we pass it multiplying to 0, which is equal to 0. And then we add the 2 to find our result of x equal to 2. Now, going with y, we make x equal to 0. So here we have minus 0 minus 2 over 0 minus 1 equals at the end in 2. As two negatives being divided make up one positive. Although we have a result for x and y, that it's not our x or y intercept, we have to put them as points. So here, for our x would be 2, 0, and for our y would be 0, 2. And that is our x and y intercepts respectively.
Well, the next process is the symmetry. And in case to be an with even symmetry, f of x should be equal to f of minus x. So we have that x minus 1 over x minus 2 is our f of x, and f of minus x should be minus x minus 1 over minus x minus 2. So here we can see that they're not the same, so there's not an even symmetry. And then we come to the next, that is the odd symmetry. So f of x should be equal to minus f of x. In this case, we still have x minus 1 over x minus 2. And in this case, it is equal to 1 minus x over 2 minus x. Therefore, it's an odd symmetry that it has. Well, now in the case of the vertical asymptote, we only need to see when x can be. So I am going to write it.
Y cambias x por 1 y dale un lado. Sí.
Okay, so in this case it's easy because in the denominator, so it could be 0, it's 1. So here we have 1 over 0, this does not exist. So in this case the vertical asymptote will be x equals 1.
Okay, now for the horizontal asymptote, it's going to get a little bit more tricky. We have the same function as before, f of x is equal to x minus 2 over x minus 1, and we're going to evaluate this function to the positive, when x approaches positive infinity. Okay, so in order to get closer to finding our horizontal asymptote, this is what we're going to do. We're going to divide.
What is this guy doing? Does he even know about math? I mean, look at his x's. He even forgot to divide by x the x and the minus 1. Does he even know what he's doing? Let's just skip forward, see if he makes it.
Infinity over infinity is 1 minus 2 over infinity. As we know, everything divided by infinity is equal to 0. So 1 minus 0.
Over 1 again, minus 0 again, because we're dividing by infinity. This is equal to 1. Our horizontal asymptote will be equal to 1.
Equals to 1. So, in order to find our first derivative, we'll have to apply our quotient rule. We already know that. Here, so two different variables being divided, we'll separate that into h of x over g of x, h of x being x minus 2 and g of x being...
Oh my god, he's just so boring. Will you shut up about derivatives? I mean, you're good looking and everything, but please man, let's just go right to the end.
Here the x's cancel out, minus 1 plus 2 is 1, so it's 1 over x minus 1 squared, and this is our first derivative.
Well, now it's going to be the ID test of the first derivative, and in this case we will use 1 because when x1 there's no point, so we will have like, we should evaluate to 1. So we have minus infinity, 1, and infinity. So we are going to take a number that is positive, bigger than 1. So when it's positive, it will always be positive. And when you take a number that is lower than 1, less than 1, it will always be also positive. So when it comes from the negative, it will go upwards, and when you come from the positive side, it will go upwards. So we don't have neither a maximum point or a minimum point. Well, now in the case of the second derivative, we have the first derivative of our function, and so it can be easier to derive. I'm going to pass the x to the denominator, to the numerator. So it will be x, f prime of x equals x minus 1. So it ends like this. Now we're going to derive with the chain rule. And we have this because we first take the minus 2 to multiply this, and the derivative of the inner part, that is 1. So minus 2 over x minus 1 cubed.
Okay, now for a concavity test, we're going to do the exact same as we did with the RID test first. But now we're going to take a function, our second derivative of minus 2 over x minus 1 to the cube. And same as before, now x will have the value of 1, because when it's equal to 1, the function does not exist. So here we have R0 or DNE in this case. Now, when we have a negative value, or a value that goes from 1 to negative infinity, we will see that we'll always get a positive result. However, not like last time, now when we put a positive number instead of x, we realize that we have a negative result. For example, if we substitute with something like 5.
So when x is equal to 5, this
as we can see now, our result is negative, and so will be with any other number greater than 1. Okay, now with the function of our second derivative drawn, which I just forgot to write, minus 2 over x minus 1 to the cube. Right. There it is. And with our table, that we can see that our concavity is upwards from the negative to infinity, from negative infinity, and downwards from our positive infinity. And that is what we can find with our concavity test.